Section 8.3 is on page 578. Talks about applications to physics and engineering. We're going to pick one application. There's another one, but we're just going to talk about one. And it talks about centroid, or center of mass. What the center of mass is a point on a lamina that balances the lamina out. Meaning, if you could figure out what that point is, or where that point is, and put a pin right there, and have this thin plate rest, it will balance out. And the formulas are given on your formula sheet. You just need to apply it. It turns out, to figure out what x bar is for this centroid, it's 1 over a, the integral from a to b, of x times the function f of x that describes this lamina, and y bar is 1 over a times the integral from a to b of 1/2 f of x squared dx, where f of x is what describes this lamina, where this a is actually just the area, the integral from a to b of f of x dx. The idea is really simple and not that complex. That's why I'm not spending a lot of time on the theory. It does come up in the next class, a bit more relevant than it is right now. So if I take right there, y equals sine of x, let's say you run 0, let's say that's 1. So the sine wave looks like something like this, and it continues on, but I'm not really concerned because I just want zero to pi basically. Well, first I need to find that area. That area is actually the integral from a to b of the integral from a to b, which is 0 to pi, of sine of x dx. That's negative cosine of x evaluated from 0 to pi. That is negative cosine of pi plus cosine of 0. That's minus a negative 1 plus 1. That's actually 2 units long. Okay, no problem. To find x bar, again, these formulas are provided. It's 1 over a, the integral from 0 to pi, identical. And here we could see that we're going to run vertical. So that's going to be sine of x dx times x. Well, let u equal x, du is dx. Let dv equal sine of x dx. V will be negative the cosine of x. So u times v minus the integral of v du. That is 1/2 negative x cosine of x plus the sine of x evaluated from 0 to pi. That is 1/2 negative pi, cosine of pi is negative 1, plus sine of pi is 0, minus, if you put a 0 there, that's a 0, and sine of 0 is 0. So basically, I'm getting a positive pi over 2. I got x bar. So far, I got it to be pi over 2, which says, hey, that should make sense. It's along this line. That's where you're going to put the pen, so that when you take this clay piece of fixed width, it would balance out. Now, to figure out where y bar is, y bar is the integral, is 1 over a, the integral from 0 to pi of 1/2 f of x squared. And if you recall how that works again, from area 5a, y bar is 1/4 the integral of sine squared of x dx from 0 to pi. Y bar is actually 1/4. Isn't that Isn't that 1 minus the cosine of 2x divided by 2 dx? Wouldn't that be 1/8 times x minus the sine of 2x divided by 2 evaluated from 0 to pi? And what would that be? Wouldn't that be 1/8 into pi minus sine of 2 pi is 0, minus 0 minus 0, so it is pi over 8. By the way, pi over 8 is roughly 0.4. So if you go along this line, if this is 1/2, 0.4 is about right there. That would be the center of mass for this problem. That's where you put the pin, and this will balance out. Here we're dealing with uniform width. In 5C you deal with non-uniform width. Here you're dealing with uniform material as well, in which the spread of the material is identical, like it's all the same wood or paper. In 5C you would deal with non-uniform material as well. Have another problem, so I'm doing one of each. This is, again, it has two main ideas. We're focusing on one. We're not going to focus on the other. Find the center for the region given by the curves. Okay, here it is. Well, let's see how the curve look. They want us to look at x cubed 0, 0, 1, 1, 2, 8, so something like this. Zero, 2, 2, 0, so they must be talking about which region. Well, it's either this region or this region. When they say take y to equal 0, now the only fixed area that's finite is actually this area. Alright, and since my formulas are in terms of x, I could switch them to y, but then I have to switch everything. Let me go ahead and keep it as is. Area is the integral. And how does that work? How do you figure out where that point is? You take x cubed to equal, isn't that y equal 2 minus x? So the only factors are 1 and 2. 1 works, right? Because f of 1 is 0, so 1 works. That's 1, and that's all you need. You know this is already 2. So how does that work? Area is going to be the integral from 0 to 1 of top minus bottom, that's x cubed dx, plus the integral from 1 to 2. And here you'll be looking at the top, 2 minus x dx. The area is actually x to the 4th over 4 from 0 to 1, plus 2x minus x squared over 2 evaluated from 1 to 2. That is 1/4 minus 0. That is 4 minus 2 minus 2 minus 1/2. That is 1/4. I don't know. This is there. That is 1/4 plus 2 minus 2 plus 1/4, those 1/2. So that's 3/4. Okay, not bad. Now what? How do you find x bar? Well, x bar is going to be 1 over 3/4, the integral from 0 to 1 of x times x cubed dx, plus the integral from 1 to 2 of x times 2 minus x dx. Pretty much once you do this, you're pretty much set. That is 4/3 times, by the way, it should go like this. This is x to the 4th, so that's x to the 5th over 5, evaluated from 0 to 1, right? Plus, and that's going to be 2x minus x squared, so that is x squared minus x cubed over 3 evaluated from 1 to 2. So that is 4/3 times 1/5 plus 4 minus 8/3 minus 1 minus 1/3. So that is 4/3 times 1/5 plus 4 minus 8/3 minus 1 plus 1/3. And what is that? That is 4/3 times, and let's see, 3 plus 1/5 minus 8/3 plus 1/3 is minus 7/3. So this is 4/3 times all over 15. That's 45 plus 15 minus 35. So that is 4/3 times, that is 60. 60 minus 25, 25 over 15. And 25 over 15 really reduces. That is 4/3 times 5 over 3. That is 20 over 9. So I'm getting x bar, y bar to be 20 over 9. 20 over 9 is... okay, something's not right. Okay, I think I got it. Let me redo this really quick. Let's look at this graph. And let's put it up there. And let's say that's 1, that's 2, and that's 1. So y equal x cubed. Y equal 2 minus x squared. So we're talking about this region. So we could just see it better. There we go. And we figured that that was 1, not a problem. So here, the work was fine. Let me just take this. This is what we did in the beginning and put it up there. That's not a problem. But this here, let me redo this part. That's the part I messed up on. Actually, it was right here, this product. And we know why it can't be 20 over 9, right? Because 20 over 9 is bigger than 2. The centroid has to be inside of the region. So that's 4/3, and this was my mistake actually, over 15. That's 45. That is a 3, not a 5. And this is a 35. That one's correct. So this is 4/3 over 15. That will be 48 minus 35. 48 minus 35. That's 3. 23. So this is... okay, no need to rush. 13, you guys. Say something. So that's 52 over 45. That's pretty good. 42 over 55. That's 52 over 45. That's 1 point some. Where's my calculator? .16. So it's pretty much 1.5, 1.1, 1 point, so it's about right there. Okay, and the y bar, well, let me set that up for you. How does that work? If you want to figure out what y bar is, y bar would be 1 over, again, 3/4 times the integral, and it's going to be from 0 to 1, and it's simply 1/2 x cubed squared dx plus the integral from 1 to 2 of 1/2 2 minus x squared dx, and you could finish that problem off, and there it is. And there's your homework. I'm giving you 4 problems, 2 each. Alright, and that concludes section 8.2.